Okay, let's see if I can help you review a little bit of polar graphing. If you have your notes from last year, or if you can find somebody with notes this year that you could copy, that might be helpful. But you really aren't going to have to be as fast. The graph themselves is not going to be the focus. It's going to be more of what we do with the graphs. So let's start off with r equals 1 plus 2 cosine theta. I don't expect you to remember what that looks like. As long as my coefficient in front of theta is 1, which it is in this case, I'm just going to put the quadrangles 0, pi halves, pi, 3 pi halves, and 2 pi in. I'm going to assume that everybody can see where I got these values from. They're just unit circle evaluations. So now let's get into graphing. When I am pointed towards 0, 0 radians or degrees, so I'm pointed in this direction, from the center I have a radius of 3. So there's my first point. When I am pointed toward pi halves, my radius is 1. When I'm pointed toward pi, here's where things get interesting. My radius is -1. How can that be? Well, the length is still 1. The length is at -1. The direction is negative. And you're used to that when you go left and down in rectangular form. It's not a length, it's a direction. So I'm pointed toward pi, but instead of going toward pi 1, I'm going to go back away from pi. I consider it walking backwards. If I'm faced toward pi, I walk backwards towards 0. 3 pi over 2 is at 1 and then back to 3. And if we were to put more points in, you would get a better definition or a better defined curve, but this is basically what it looks like. It goes through here. It does go through the center. It makes a loop, comes back through the center, and then back around. The one thing that's going to be really important for you to be able to identify on this graph is what range of theta values did it take for you to get the full curve. In this case, it was 0 to 2 pi, which is, you know, pretty commonplace. Okay, go back, go away. It's not. Please collapse, go away. There. Sorry, guys. So 0 to 2 will give you the complete curve. But something else that we might be interested in finding out, let's say we want to find the area just under the loop or inside the loop, I'm going to need to know the angles that form the loop. So if you set your equation equal to 0, you can find when it actually passes through the origin. So you're going to get the trig equation, cosine of theta equals -1/2. I put your ASTC in here so you can see that your angle is going to be in the second and third quadrant, because that's where cosine is negative. Your reference angle is pi thirds, so your answers are 2 pi thirds and 4 pi thirds. So if we had included 2 pi thirds in here, we would have actually gotten a radius of 0, and if we had put 4 pi thirds in, we would have gotten a radius of 0. So at 2 pi thirds, you're at the origin, you come around at pi, and then back to the origin, and then you continue the curve. So hopefully that'll give you kind of an idea of what those type of curves look like. Another popular polar is the one that we call a rose with petals. And there's some basic rules on this. The 3 that's in front of the sign is going to give you the petal length. If the coefficient is other than 1, you're going to form these petals. When I see 2, if you remember, if the coefficient is even, it doubles the number of petals. So I'll write that down for us. And so again, I've included your values, but notice this time, instead of just jumping from 0 to pi halves, because of the 2 here, I cut the pi halves in half and put the pi fourths angles. So pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. So let's graph the curve. 0, 0. So we're at the origin and we don't move at all. Pointing toward pi fourths, we go 1, 2, 3, and then pi halves has us back to 0. And so this creates that first petal. That's really important, that first petal. Then from 3 pi fourths up here, we get negative 3. So again, instead of drawing that petal in the second quadrant, I'm going to draw it backwards into the fourth with a radius of negative 3. And so I'm going to go from here to here, around this way, and again back to the origin at pi. So here's where I am. I'm still at the origin. 5 pi over fourths puts me down here into the third quadrant. My r is positive, so I'm going to stay down there, and I'm going to draw my third petal. And then when I'm faced to 7 pi over 4, notice again my r is negative, so that's going to take me back to the second quadrant. So there's our petal. And last year, you didn't think about the order in which this polar graph was traced. You just probably went ba-boom, 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 ba-boom. Done. You got a nice little flower. But we're going to see that this really traced into the first, down to the fourth, into the third, and up through the second. So it did take 0 to 2 pi to create the full polar curve. But if we only wanted one petal would be right here where we have from 0 to pi halves. If our problem is going to ask us to find the area under one petal, then we're going to set up our angles from 0 to pi halves. If it wants all the area under the full rows, you would probably only do one petal and multiply it times 4 because they're all the same length. Okay, so hopefully that helps. If you're wondering why I would even bother talking to you about 0 to 2 pi, because it seems like everything should be 0 to 2 pi, what if I just have r equals 4 sine of theta? And I'll make my own little graph here. So for that one, we make our t-chart. And I'm going to go 0, pi halves, pi, 3 pi halves, because why not? There's a 1 coefficient in front of theta, so that seems to be what I told you to do in the first problem. So the sine of 0 is 0. The sine of pi halves is 1. So times 4 is 4. Pi is going to get us back to 0. 3 pi halves, then it's going to be negative 4, and 2 pi will be back to 0. So I start here, I go up 4, and then I'm back to 0. So I get this one petal effect, and to be honest with you, that one petal is a circle. And then when I'm down here at 3 pi over 2, my r is negative 4, so I end up lapping this thing twice. Well, if you're finding area, and again, area is going to be integration, and you go from 0 to 2 pi, you're actually going to get double the amount of area because you will have lapped it twice. So for this specific polar curve, we get one, we trace it once from 0 to pi, not 0 to 2 pi. Hope it helps. I'll see you tomorrow or either Monday.